Tutorial 2, Aircraft Structure. This presentation will discuss the design of aircraft. Knowing the benefits and limitations of each type of construction and material can help make a safer pilot. When an airplane is in flight, there are 4 forces at any given time that act on the plane. These forces are thrust, drag, lift, and weight. Thrust is generated by the engine, power plant, and the propeller, which pull the plane forward through the air. Drag is the next force and acts opposite the aircraft. While thrust pulls the plane forward, drag slows the plane down and is caused by air hitting the body of the airplane. Lift is generated by the dynamic effect of the air acting on the wing and acts perpendicular to the flight path. Weight opposes lift and is caused by gravity. Everything in the plane, pilots, luggage, fuel, and even the plane itself are pulled down by gravity, causing the aircraft to have weight. Lift and weight always act through the airplane's center of lift and center of gravity, respectively. Center of gravity is the point on the aircraft in which, if the airplane were suspended, it would remain level. The position of the center of gravity is very important for aircraft and can be affected by the installation of onboard equipment, aircraft loading, and other factors. When the center of gravity is too far aft or too far towards the rear of the aircraft, the plane will have a tendency to pitch up, which can cause the plane to stall. While having the center of gravity too far forward, the plane will have a hard time getting off the ground, and the nose will tend to pitch down. Aircraft move around 3 different axes. The lateral or pitch axis is a line drawn from the wingtip through the plane's center of gravity to its other wingtip. The longitudinal or roll axis is drawn from the nose to the tail of the aircraft, again passing through the center of gravity. And the vertical or yaw axis is drawn vertically down through the plane's center of gravity. Although airplanes are designed for a variety of purposes, most of them have the same major components. Most airplane structures include a fuselage, wings, an empennage, landing gear, and a power plant. The fuselage is the central body of an airplane and is designed to accommodate the crew, passengers, and cargo. It also serves to connect all the other main components of an aircraft. Pictured above are 3 different types of fuselage structure: truss, semi-monocoque, and monocoque. There are many different designs, shapes, and sizes of wings used by the various manufacturers. However, their main purpose is to lift the plane into the air. Above are 2 different designs. The plane in the upper left has 1 wing and is called a monoplane. The plane in the lower right has 2 wings, referred to as a biplane. Wings can be placed above, on, and below the fuselage. These different wing placements are referred to as high, mid, and low wing planes. Most high wing planes have external struts to help dissipate the wing's load to the rest of the plane. The picture above shows the general construction of a modern wing. The ribs, stringers, spar, and skin all give the wing structure. The fuel tanks in most modern airplanes are also contained in the wing near the fuselage as part of the wing or in flexible containers. The front of the wing is the edge that the wind hits first, also known as the leading edge. Attached to the opposite side of the wing, or trailing edge, are 2 control surfaces called the aileron and the flap. Wings are exact mirrors of each other and contain the same control surfaces on both sides of the airplane. Ailerons extend from about the midpoint of each wing outward toward the tip and move in opposite directions to create aerodynamic forces that cause the airplane to roll. Flaps extend outward from the fuselage to near the midpoint of each wing. The flaps are normally flush with the wing's surface during cruising flight. When extended, the flaps move simultaneously downward to increase the lifting force of the wing for takeoffs and landings. The pictures above show different styles of flaps. The basic section shows a retracted flap, and the 5 pictures below it show different styles and their effect on airflow. These different designs are discussed in more detail in the flight controls lesson. The empennage consists of the entire tail of the aircraft. There are fixed parts, such as the horizontal and vertical stabilizer. There are also movable parts, such as the elevator, one or more trim tabs, and the rudder. The rudder is attached to the back of the vertical stabilizer. During flight, it is used to move the airplane's nose left and right. The elevator, which is attached to the back of the horizontal stabilizer, is used to move the nose of the airplane up and down during flight. Trim tabs are small, movable portions of the trailing edge of the control surface. These movable trim tabs, which are controlled from the flight deck, reduce control pressures. Trim tabs may be installed on the ailerons, the rudder, and/or the elevator. A second type of empennage design does not require an elevator. Instead, it incorporates a one-piece horizontal stabilizer that pivots from a central hinge point. This type of design is called a stabilator and is moved using the control wheel just as the elevator is moved. Stabilators have an anti-servo tab extending across their trailing edge. The anti-servo tab moves in the same direction as the trailing edge of the stabilator and helps make the stabilator less sensitive. The anti-servo tab also functions as a trim tab to relieve control pressures and helps maintain the stabilator in the desired position. Landing gear are what support a plane when it is parked, taxiing, taking off, and landing. The most common type of landing gear are wheels, shown on the upper left. Planes can also be fitted with floats, pictured in the top right, which let planes land on water, and skis, pictured below, are used to land on snow or ice. Airplanes with conventional landing gear are sometimes referred to as tailwheel airplanes. When the third wheel is located on the nose, it is called a nose wheel, and the design is referred to as a tricycle gear. The power plant usually includes both the engine and the propeller. The primary function of the engine is to provide the power to turn the propeller. It also generates electrical power, provides a vacuum source for some flight instruments, and in most single-engine airplanes, provides a source of heat for the pilot and passengers. The engine is surrounded by a cowling, which makes the engine more streamlined and provides a way to duct air over the cylinders. The propeller mounted on the engine translates the engine's turning force into thrust. The propeller may also be mounted on the back of an aircraft and used to push the aircraft forward. A propeller is a rotating airfoil that produces thrust through aerodynamic action. A low-pressure area is formed at the back of the propeller's airfoil, and high pressure is produced at the face of the propeller, similar to the way lift is generated by an airfoil used as a lifting surface or wing. This pressure differential pulls air through the propeller, which in turn pulls the airplane forward. Aircraft have been made from all different materials, including wood, cloth, steel, aluminum, and more recently, composite materials. Pictured above is a fuselage made from a truss-style structure. This design is not used very often because it lacks a streamlined shape. As technology progressed, designers started covering the truss members to make the aircraft more streamlined and have improved performance. Shown above is a monocoque fuselage design. This design relies on the skin of the aircraft to take most of the load. The skin is stretched over internal bracing and reduced the need for many struts inside the wing. This type of aircraft fuselage design combines the monocoque and truss designs and is called semi-monocoque. The skin still supports some load, while the stringers also carry load. This improves the strength of the fuselage over the monocoque design. Composite materials are fine fibers arranged in a matrix system held together by glue such as epoxy and polyester resin. The fibers are most commonly made from carbon fiber or fiberglass. Fiberglass has good tensile and compressive strength, good impact resistance, is easy to work with, and is relatively inexpensive and readily available. Its main disadvantage is that it is relatively heavy, and it is difficult to make a fiberglass load-carrying structure lighter than a well-designed equivalent aluminum structure. Carbon fiber is generally stronger in tensile and compressive strength than fiberglass, and has much higher bending stiffness. It is also considerably lighter than fiberglass. However, it is relatively poor in impact resistance. The fibers are brittle and tend to shatter under sharp impact. Composites have their advantages. They are lighter than materials like wood and metal. They are smoother, which allows for less drag. They do not corrode or rust, and they flex without suffering from things like metal fatigue or crack growth. Some disadvantages of composites include the difficulty in spotting damage. Composite materials, when impacted, may show no signs of damage on the surface, but underneath they may have extensive cracking. The above pictures show damage that can happen when a composite material is impacted. Another problem with composites is the fact that excessive heat can cause the resin to weaken. Heat from sunlight on pavement or a small fire, even when extinguished quickly, can cause damage. Also, chemical paint strippers are very harmful to use with composites. During a lightning strike, the aircraft needs to dissipate the energy around the body of itself to a safe level. Electricity generally flows around the skin of the aircraft because it offers the path of least resistance. Fiberglass, for example, is an electrical insulator, which makes it not able to diffuse electricity well. To handle this, a fine metal mesh is often placed around the outside of an aircraft. Switching out the old instrument panels with new instrument panels, as shown above, makes planes safer and more reliable. Old instruments relied on analog gauges to give readings. In more modern aircraft, these analog gauges are replaced with LCD displays that give the pilot more data than the analog gauges and gives the information in a more compact layout. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.